First off, I'd like to thank the organizer for organizing such a wonderful workshop. Lots of very interesting talks, and also we got the good news we're getting free food after the session, so I hope everyone's now awake and excited. So a little disclaimer, I'm going to switch gear a little bit from most of all the other talks where the focus is to develop a algorithm, with certain properties, it's faster, etc. So, well, we also have worked on a fast algorithm, the asynchronous second-order method, which you may have seen in a poster yesterday. And I'm not going to talk about it here, but if you're interested about it, I'd be happy to talk with you offline, or my student, Samira, sitting over there. So this talk, the focus is to develop a new framework of viewing or evaluating distributed algorithm in which the keywords are here, balancing communication and computation. So the focus is going to be slightly different from all the existing talks. So just bear with me to see why we need to look at the trade-offs between communication and computation. Okay. So these are my co-authors on the paper. So Albert Ragul, these are PhD students at Northwestern, and Tish has graduated. He's now working at Salesforce in the Bay Area, so he has much better weather than we do. So these work actually started as a course project. Okay? And these are the students who took my class on distributed optimization. So part of the class, we have a independent project at the end, and where they were developing interesting theory. So why was that relevant? Okay? Because, so let me just start with the motivation. Okay? So these are things I was teaching in class, right? So I'm going to work with the same problem formulation, which we have seen many times in this conference, minimizing summation of FIs related to empiric risk minimization, and a lot of other interesting applications. So here are some interesting applications: sensor networks, robotic teams, and machine learning. And a lot of us in the room have worked on this problem. And typically, what happens is we develop an algorithm, and at the end, we plot this numerical results, right? This is actually from one of my own paper. So what happens is you have compare with existing algorithm one in the literature, another algorithm in the literature, and then you have your own algorithm, right? And that's going to have a much faster decay in the error, whatever, however you want to measure it, and you plot it against number of iterations, right? This looks familiar, right? So this was how the standard literature was going, right? And then sometimes instead of iterations, we also count total of clock time or CPU time. Sometimes we count in number of communication routes, right? So these are all things that we have seen. But let's take a step back. So some of my students were asking, what exactly should we plot? And for me, it was obvious. You plot it against number of iterations. But then if we look at the application we actually motivate this problem under, all these applications has very different focuses. So for instance, if we look at the sensor network, so maybe these are sensors that's deployed out there to collect data. They are not in really big hurry to get to the end of the optimal solution. They want to get there, but time is not an issue there. Rather, maybe their communication protocol is very expensive. Maybe it relies on wireless communication or infrared or whatever their protocol is. So maybe there the communication is a bottleneck. And instead of looking at iterations, we should really try to minimize communications. Right, so then, okay, fine. There are works that aims at, like, we have seen a few communication-oriented talks, such as the Keith's talk yesterday or Nali's talk from yesterday. They were looking at the communication ones. Great. But what about other applications? So robotics, for instance. These are things that's moving around, and once you deploy them from base station, they'll be on their own for a while. They have to talk to their neighbors, figure out their local computation, and hopefully go into swarming or certain goal. We also have seen a few robotic talks there, right? They have different goals. And then the constraint there may be the battery, because once they are deployed away from their station, they're on their own. They have to finish the task before the end of their battery life. Right? So maybe this is not the best picture because these robots have very big battery packs. But in other instances with those smaller ones, like insect-sized ones, there the battery or power is really a big constraint. and the battery can be drained from either communication or computation when we are doing the optimization algorithm, right? So both of them are important. And then this last one I have as a large-scale computation, so maybe think about it as a data center or cluster. So I actually personally went into Northwestern Data Center and asked them, how important is communication overhead to you? Surprisingly, I thought they were going to come back and say, we really don't want to do any communication, and because they're far away from each other. But turns out, at least in Northwestern, all of these these nodes are connected through very fast Ethernet cables. They're like physically connected. So there, the bandwidth is very large, and communication doesn't take much time. The bottleneck is in computation. So, but the story could change if we are running, let's say, a large-scale problem on the cloud, right? For instance, if you want to rent some servers from Amazon, you can also pick some server, let's say in US, some server in Tokyo, some server in Europe, and in there, the communication would be very laggy. So if you still want your algorithm to perform well overall, then you would have to be careful thinking about how much communication is involved. So long story short, different applications has different needs. Right? Some of them needs more can tolerate a lot more local computation. Others, they really don't care about communication. So the algorithms that we are mostly developing, and I myself is a culprit there, we only look at the time complexity, right? So in this iteration, there could be communication and computation, and somehow they're all bundled together, okay? So this work is motivated by the need of an evaluation framework for different algorithms that should reflect the features of different applications. Okay? So eventually, the goal is to construct a environment, a flexible framework where we can develop algorithm. So you would have maybe one idea for the algorithm, but depending on the application, you would tune the algorithms for specific application and be adaptive for the environment. Okay, so that's the goal here. And then so I should say this is still in the early stage of this problem, or of this project. So we're going to look at this one particular problem formulation, which we have seen a lot in this workshop. It's a consensus optimization. And so we're minimizing summation of fi of x. And to make it distributed, we introduce local copies. And then after a certain algorithm at optimality, eventually we're going to all agree on the same value, and also it's the optimal value. Right? So that's the same standard setup. All right. So just let me set some of my notation straight. So we have a connected graph. I'm working with undirected graph for now. And also this zx equal to x is my constraint for consensus. Essentially, typically people use wx equal to x, where w is the W stochastic matrix, the consensus, standard consensus matrix. So nothing fancy is happening here, except I'm working with xizing RP, so I have to do the canonical product right here. So the Z matrix is essentially a higher dimensional version of the W consensus matrix, right? So it's the standard constraint right here. Okay. So this is a problem we're going to focus on. And let's see what are some examples of literature. There's a lot of literature working on this problem. So I listed a few here. There's sublinearly convergent, linearly convergent, superlinearly convergent, primal algorithm, dual algorithm, primal dual algorithm. I have no space to list all of them. So the first two categories, these rates are all with respect to time. Right, as I was saying, that's the typical plot where you plot against iterations. And then the third bullet point here, these are the communication efficient algorithms where people think about communication. But rather there, the goal is to either so depending on which work, so some of them look at to minimize the total amount of communication. They don't care about the runtime at all. So maybe it is appropriate for some of the applications. Or others says, I'm going to have a goal in certain time, and underneath which my communication would be proportional to that time, etc. So they all fall under very specific setup in terms of this communication aware or communication efficient method. Okay? And then the last Cross-off methods are asynchronous methods where in the distributed setting, all the agents do not have to update at the same time. Okay, so these are a rough breakdown of the existing literature, and I'm sorry if I missed some of the great work. But this is more important. So no matter which of the categories we're looking at, in general, each iteration has two components, right? Communication and computation. And so it's a combination of some of them. So personally, I also worked on second-order methods and first-order methods. But when we plot the iteration count, it's all the same, right? It doesn't matter if you computed a Hessian or a gradient or took a product of Hessian and gradient or did 2 rounds of communication versus 1. It's all counted as one iteration. And then when we plot it, it's against the total number of iterations. So this work is looking at breaking down the communication and computation component of the algorithm and say the true cost actually should involve both number of communications and number of computations, okay? And for the lack of a better model, we just said in our model, in our evaluation framework, we're going to say the true cost is going to be summation of a linear combination of these two, okay? So exactly how large is CC and CG? So cost of communication and cost of G is this gradient. So computation, these would depend on the application. So for certain applications may have a much higher CC versus C, cost of communication versus computation. So these are parameters that depends on the particular application. This is what we're going to use as a measure of cost, and later when I show you numerical results, this is what I'm going to be plotting against. All right. Okay, so the goal of the project is to develop a framework that is independent of method. So whatever method you have there, we should be able to lift it up into fit different kind of application needs. Okay, and then in terms of balancing the communication and computation, exactly what is balanced, well, that depends on the application. Okay, so remember the CC and CG come from the applications, and well, hopefully the method will converge. So we'll also guarantee some theoretical convergence, and then so this framework should be very general. And also, we will aim to look at some numerical studies to see how the twisted or modified version of the algorithm compare with their baseline in different environments. Okay, so and in this, so that's the overall grand scheme of the project. And as I said, we're in the early development phase of this project. So we're just looking at one particular algorithm, the distributed gradient descent or subgradient descent algorithm, and looking at how that can be made into different communication and computation aspects. So we're going to focus on this DGD algorithm for this talk, and then design a flexible first-order method that decouples the communication and computation based on DGD. And then we're going to look at the theoretical and empirical performance of the proposed algorithm. And then the byproduct is we managed to have a DGD-based algorithm with exact convergence, meaning it goes to the optimal solution instead of a neighborhood of the optimal solution with constant step size. Okay, so that is more or less a byproduct. So if you're interested in the details of the paper, we'll have it up within this week or so. We're still doing some final polish, and we also need help naming the algorithm. So I'll point out when we get to the algorithm, and if you have great names, let us know. Okay. All right, so what is still ongoing, and I'm not going to talk about it, so multiple gradient, I'll explain that in a bit, but this talk is going to be focused on DGD, and we're also working on applying this similar framework into other algorithms, such as extra and network Newton and other asynchronous methods. Okay? All right, so what I'm going to do next is to give you 2 different variants of distributed gradient descent. Okay, so this kind of shows our progress throughout this project, and you'll see a few byproduct algorithms. They will be also interesting on their own. Okay, So let's just review a little bit the DGD. So distributed gradient descent or subgradient descent if the problem is non-smooth. Oh, we are going to focus, since it's an easy or a first step towards the grand scheme, we're going to look at this easy case where the function is Lipschitz gradient and has Lipschitz gradient and is strongly convex. Okay, so that's why it's DGD, not the subgradient version. So DGD has been around for a while and was developed in the 80s and then got popularized and with many follow-up recently. And this is a short list of the representative work. So we have seen this algorithm many times through the workshop. I'm not going to dwell too long on this, but essentially DGD has two components. One is you take an average with your neighborhood. The other one is you take a gradient going down in your own direction, right? So, and then these are the matrix notation, the shorthand notation. So remember, Z is related to the consensus matrix, right? So the high dimension of consensus matrix. So Zx here is the average, and then gradient of F is the gradient direction. Okay, so what do we know about DGD in terms of convergence? If we diminish the step size alpha right here, so if as the algorithm evolves, we kill the step size, then we get a sublinear convergence to the optimal solution. Or if we keep the alpha as a constant throughout the algorithm, then we get a linear convergence to the neighborhood that's determined by the size of your step size. So essentially, there is a trade-off in the algorithm. If you have a large step size, you make progress fast in the beginning, but you cannot go to the exact optimal point. If you have a small step size, then you will have a smaller neighborhood once you converge, but the algorithm is slower overall. Right, so these are all well-known results. Now, we started staring at this vanilla version of a distributed algorithm and then ask ourselves, is it necessary that we always do one consensus and one gradient? It seems natural to do, and it makes sense because there are two objectives. You try to agree with your neighbors. You are also trying to go down in terms of your own objective function. So, well, but the answer is obviously no, and we have seen a few talks where you do mini batch and you look at take a few gradients locally first, right? So, and in our case, we're going to also do a few communications, so we could choose between either do a few communication or a few computation steps locally. Okay. And then the follow-up question, so if the answer to the first question is no, then what is the interpretation of the methods that we do more communication or computation? Okay? And what are things we can say about convergence? And more importantly is how these variants perform in reality. Okay? All right, so our first attempt, so this is the first algorithm I'm going to present, is DGD to the T, which is essentially we're saying instead of averaging with your immediate neighbors, we're going to average with your T-hop neighbors away. Okay, so growing the neighborhood that you're talking to at every single iteration. So you may say, okay, this is a lot of communication per round. Yes, that is the case. Okay. So as I said earlier, we're not doing many gradient steps per iteration for now, but the same framework can be easily flipped to do more gradient steps. For illustrating purposes, I'm talking about doing more computation step at a time. Okay? So Z to the T says we're going to first average with many neighbors, many agents in the network, and then take a gradient step with a constant step size. So it's essentially the same as before, except we're getting this red T right here. Okay. All right, and then what can we show about this particular variant of the algorithm? So we're using these two assumptions. The first one is on the objective function. We're assuming they are nice in terms of the first order. So they are strongly convex and has Lipschitz gradient. Okay, and then we're not going to worry too much about how strong these assumptions are for now. We just wanted it for a demonstration of purpose. So the second one is another standard one, the mixing matrix W, which the Z1 is built on. It's symmetric and doubly stochastic. As I said, I'm looking at undirected graphs, so things are much nicer. Otherwise, you may need to use push sum or sum of the or Aldo's construction of networks. So there may be ways to extend this to directed or not so nice communication graphs. Okay? And then these are definitions we need for the proof. Essentially, the bar ones are the average ones. Okay? And then I'm not going to bore you too much with the proof. This is actually taken from one of Wattau's paper on showing the linear convergence of DGD under the same assumption, but it goes to an error neighborhood. Okay? So this is distance of the average of the average among the neighbors to the optimal solution. So it's diminishing geometrically plus a constant term here. Okay, and don't worry too much about these definitions, except the C3 depends on the alpha, the step size. Okay, and beta, I did not tell you what. Here, beta is the second largest eigenvalue of the matrix, so it's a mixing constant. Okay, all right, and then we essentially followed the same kind of proof to do for DGDT, and not too surprisingly, we need to adjust the step size that we could tolerate, and also the end result of the error neighborhood changes. I should say that here I'm showing the results in terms of the average to the optimal. You could show the same thing about each iterate to the optimal. It's essentially the same with another constant here in front. Okay. So now compare with, this is a standard DGD, and this is a DGDT variant. The only thing that has changed is the step size and also the constant of the error neighborhood. Essentially, the error neighborhood went from 1 over beta related to 1 over beta to the t. Right? Okay, so that hopefully is not too surprising, but it does show something nice in terms of we could make the error neighborhood smaller if we mix better. So that's a trade-off we get. The precision of the algorithm versus how many rounds of communication we can tolerate per iteration. Okay, so this is a constant. Every time when we run DGDT, we make it run T communications. But, so here's a big but, we cannot kill the neighborhood with increased communication. So even if we run infinitely many rounds of communications, the best this could go to is 1. Okay, so there's still a constant there at the error neighborhood. And also, the drawback is it requires extra communication per iteration. So how should we think about this DGDT? Well, it's essentially with a different underlying graph, right? Instead of talking to the immediate neighbor, we're talking to a few neighbors a few hops away. So let me go through this quickly. So if we have this graph, and this is W, so the immediate neighbors. If we do consensus twice, essentially we're talking to everyone here. That's the obtained graph. And then if we do about 10 iterations, it becomes average, complete graph with average. So essentially you do one consensus and you're about exact in terms of average. So that's why we can kill the error neighborhood. And similarly, we can do this for line graphs, so the mixing gets better and better. So let me, actually, I do want to save time for the second part and also the numerical analysis. So we ran some numerical studies of these DGD different variations. So we're doing, so the first number is the number of gradients. The second number is the number of consensus per iteration, right? So DGDT, the second number indicates how many T there is. So we ran this on a 10-node graph, 4 cyclic, meaning it's a ring, but instead of just connected to your neighbors, you also connect to your neighbors 2 hops away. So it's an expander, has pretty nice connectivities, and the condition number is 10 squared. Okay. So we want to show the effect of multiple consensus step. Okay. So now here's the plot, and here's something interesting happening. So on the left, this one is the typical plot we see. It's a total number, it's a relative error against iteration. And if I were writing a standard optimization paper, I would stop right here. Except, as we say, we were interested in looking at the true cost of it. So we made up some costs, okay? We just say the communication and computation is going to cost equally. And because we're doing lots of communication inside of, for instance, this DGD 110 is 10 consensus per iteration, right? So you see how different these two graphs look like, right? If you were to just look at time complexity, maybe you would have picked this black curve right here. But now if we were to consider both communication and computation costs, the black curve all of a sudden does not look that favorably. So this is one of the key findings we had here is by looking at different metrics of cost, your preferred algorithm would change depending on the applications. Okay. All right, so that is a warming up exercise of DGD raised to the t. So still we are saying we're essentially taking DGD, distributed gradient descent, exactly as it is, right? But we said we're going to decouple the communication and computation to give us the flexibility to tune it. So let's come back to DGD one more time and define these two operators. So essentially, one is a consensus step, the other one is a gradient step. So DGD can be viewed as these two operators put together in a not very straightforward way. So if you look at T minus I is the identity operator plus W, then you get exactly the DGD operator. Okay. So now we take a step back and say, well, it looks like a combination of T and W. Let's just put them on top of each other. Okay. So then we have this TW and WT algorithm, which is saying TW is saying we run consensus first, and then we take a gradient based on that. Or we take a gradient first and run consensus. So how different are these variants from the original DGD? Okay. So if we just compare the right-hand side, the TW version says I'm going to take a gradient at the newly mixed version. So this now has a very similar flavor to the gradient tracking algorithm or the digging or at least work on this. So, so somehow we all converged to saying we need to do something about making sure the gradient is at the right point. But okay, that's actually not where we came out. We just say we want to put the two operators together and see what happens. Okay, and then later we found out a special case of this TW and WT algorithm appeared earlier for a special case of quadratic problems. Okay. So, and the WT version is the opposite. So you take the gradient at your current local point, and then you're going to average of your gradient. So one is gradient at the newly averaged point, the other one is average of the gradient. Okay, so these are different versions of the algorithm. And for the rest of this talk, I'm actually going to focus on something based off the TW. We believe the same thing can be said about the WT. So all of a sudden you see from DGD, we can make a few different versions of the algorithm. So this will broaden the classes of tools we have. And so not only we're going to look at TW and W, so this looks pretty boring, right? I just gave you 3 different algorithms. I have 2 operators. I just somehow do things different to it. So you can think about we could also do multiple gradient or multiple consensus per iteration. So now we have this completed decoupling of consensus or communication and computation steps. And depending on your cost, whatever you prefer, you can run more computation or more communication per iteration. So this is what we mean by decoupling the communication and computation. Okay. So we're going to look at these 2 different methods. This is the part I need help with naming. Okay. So we're calling this now TWT, which is essentially saying 1 gradient and T numbers of consensus. Okay. And T is predetermined. The second one is TW plus, which is saying we're going to increase the number of consensus. And I'll tell you why we have to increase the number of consensus in a bit. So, so this is the algorithm clear. So it's pretty much same as before, except that every time you do either T number of iterations or as the algorithm evolves, you run more and more number of communications, right? Consensus. So we're going to do the same analysis under the exact same assumption as before. Lipschitz gradient, strongly convex, and doubly stochastic nice consensus matrix. Okay, so let's first look at this TWT version. So note this is different from DGDT. Okay, the subtle difference is, let me maybe come back here, is in where you take the gradient. So here we're taking gradient after the T time mixing versus DGD, the only T is here at the Z part. So at the TWT part, we can do our analysis and come up with the following conclusion. So the iterate distance to the optimal solution is decaying at this geometric rate, so C1 to Ci to the k. And then it also has this part right here. So remember, beta is the second largest eigenvalue of the mixing matrix, right? So it is bottlenecked essentially by the graph topology. And if we have a fixed t, then we run into the same problem. We didn't solve anything. We're still going to an error neighborhood. And the error neighborhood now is determined by beta to the t. All right, so I just bored you with lots of notations and then this is a new algorithm that still doesn't go to the optimal point, right? But then there is hope. What is the hope? So here, the error neighborhood now only depends on beta to the t. Before, it was 1 over 1 minus beta to the t. So there was no hope to kill that term. But now all these depends only on beta. So the natural idea is to ask, can we increase the number of consensus and then get rid of the error neighborhood? So here's the idea. We're going to increase this t instead of a predetermined t for all iterations. So this may be a little confusing. K is the iteration count. T is how many consensus we're doing at that particular iteration. Okay? So instead of a constant t for all the iterates, maybe we can increase the number of consensus steps. Okay? And then the result would be what we would kill this O of the error neighborhood, right? So then once again, we convert to another early literature that was looking at non-smooth problem for proximal-based algorithms. So it's a very different setup, but the same idea of increasing number of consensus has appeared earlier in some of the Arsu's work earlier. So, but in our case, if we keep increasing this t to the k, I'm not going to bore you with proof detail, but you can probably tell from the previous slide, as long as we have this t of k being an increasing sequence, then we can kill the error neighborhood. Right? Exactly how fast, I don't care, as long as it's increasing. So, okay, maybe I should care if I care about the rate, but remember, we're doing it with respect to cost, and that cost, I haven't told you what it is yet. So, so then here what we're suggesting is we have a way to construct distributed algorithm based on this T and W operators. And depending on your applications, you would increase this number of consensus at whatever preferable rate is to your application, and we can guarantee you convergence to the exact point. Okay? And then if, for instance, we were to increase TK at a linear rate, so meaning the first iterate, we do 1 consensus, the second one we do 2, the third one we do 3, and so on, then we can get this linear convergence to optimal point. And then the amount of work we need to do is linear in terms of gradient evaluation, but remember, we're increasing number of consensus, so you'd expect it's not so good because we may end up doing a lot of consensus. Turns out it's not that bad. It's a square of a log term, and log term doesn't grow too fast. So, so in terms of communication, this is okay, but then once again, you could think about doing, instead of TWT, you could do TTW, right? You can run many gradient iterates first and then do consensus. So we have a pretty flexible framework, but since I don't have a concrete problem to tell you what exactly should the costs be, let me just show you some simulated results in how different versions of the algorithm. So it's a little bit hard to read, but DGD is a standard DGD. This TW11 says 1 gradient, 1 consensus. And this part that's barely visible, TW101 says we're going to do 10 gradient, 1 consensus. So every iteration we're doing that. Okay? And then 110 is the flip. So this TW11K is the one in the previous slide saying we're going to increase the number of consensus at rate K. Okay? And then we also said maybe practice will be different from theory. Let's try some other ways of increasing the number of consensus. So the last two here say 11500 says we start with 1 gradient, 1 consensus. Every 500 iteration, we're going to double the number of consensus. So as we have seen earlier, we need to increase the number of consensus. Why we chose to double, it was just an arbitrary choice. You could have tried many of other things. But let me just show you what it looks like. So we first run it on a quadratic problem where kappa, the condition number is 10 to the 4, so it's a pretty ill conditioned problem. Okay, and then I'm plotting here is the cost of one communication, so cost you 1 unit for each communication and computation. Okay, so they're equal cost, and this is the DGD, and then I add a few different versions. So this green curve is when you do 10 gradients, 1 consensus, and etc. So what's more interesting happening is here when we increase the number of consensus. So if you just look at the standard against iteration curve, this green curve is doing remarkably well. Except if you look at the true cost, it's actually not as good as even the DGD because it's increasing number of communications too fast. Okay. So once again, we know this very different behavior from counting against iteration versus this cost. Okay, and then we tried a few of the other things which the theory did not guarantee linear rate of convergence, it just guaranteed convergence. But in terms of cost, these two curves are performing better. These are the ones every certain number of iteration we double the communication amount. Okay? So they perform pretty well in practice. Okay. Well, then you may ask why it's one communication, one computation, right? I just said application require different costs. So let's actually vary the C a little bit. Okay, so they're still the same candidate algorithms. Now the center one has equal cost. And the left one says we're going to incur a very high cost for computation and low cost for communication. And the right one says we're going to incur a very high cost for communication, a low cost for computation. Okay. So you can see in different costs, you end up with different behaviors and certain algorithms more preferable in one setting than the other. So one obvious example is this bright green curve, right? It's really, really bad when your cost of gradient or computation is high. But it's doing okay if your cost of communication is much higher. So it gives you a different preference over algorithms. Okay? And then we, let's see, what else do we do? So, okay, we ran this into the mushroom data set. It's a data set existing on the network, has 8,000 data points. Essentially, you classify if the mushroom is edible or not. So, and it's a logistic regression, and we just took the data set, ran it on to distribute the data points on 10 different computers, and then simulated it. And once again, we get the plots where the plot against iteration and the plot against costs are very different. So depending on the cost, you want to choose one of the, if you are using first order algorithm, you would want to vary your TW ratios. Okay, all right, so Chair just informed my time is up, so let me summarize. So we looked at the algorithm, the existing distributed algorithms, and most of them do one communication and one computation per iteration. And then we showed different versions of it. You could do multiple communication for now, but the same analysis can be extended to do multiple computation per gradient. Okay? And then in our TW algorithm, it really decouples the consensus and the computation. So we showed the nice convergence properties, and here's a comparison once again about DGD against the TW algorithm. So to balance, so coming back to my title, balancing communication and computation, this really depends on your true cost. So our goal is not to give you one algorithm, but a family of algorithms and a way to come up with a family of algorithms depending on your applicational needs. Okay? And some of the future work, well, one is to apply to other algorithms, and then to finish our work with multiple gradients. And then one thing is, so far we're just prefixing the number of communication and computations and then try it out to see how they perform. So our goal eventually is to be able to adaptively adjust the number of communication and computation towards the application. And many of the other important considerations, one thing we never touched upon is the memory access, right? We just said communication, computation. We did not talk about storage. That's one thing. And then as Aldo was pointing out, maybe sending out the entire block is too costly. What if your communication has only components of it, and then quantization, in fact, also dynamic networks. So these are all interesting directions to extend. Okay, and with that, I'll conclude and be happy to take any questions.
We have time for some.
So even without the adaptive methods, typically when we go to deploy these kinds of things in practice, we can measure the communication and computation cost, especially if you're thinking about it in terms of how you spend the battery. And what we want to do is say something like, I have a fixed utility that I have to meet, or I have a fixed cost that I cannot exceed, often, or sometimes both. And then there's a step of like translating that to the parameters that you should use. Is that straightforward here? Or do you
It's
just
not
have to do a
straightforward.
Whole lot of
So
simulation and choose one?
hopefully not simulation. We're developing theories for that. So essentially, you're having another optimization outside the optimization, right? You're trading off choosing the parameter, and meeting your goal of certain utility would be one of the constraints. That depends on the algorithm. So we are working on how to develop theory to automatically do that part. Yeah, Mert?
So I was thinking that maybe memory can be added to your code.
Yeah.
Because partially, basically, suppose that you can double the memory, like you can store 2 vectors, then you wouldn't have to do any communication to achieve the same rate.
Yeah. So memory is one big issue. We're still thinking about how to incorporate it. So since I guess VRG versus Saga or other algorithm, that would pose a nice trade-off between memory. But so we were thinking about adding to the cost one extra component of memory access times a constant, and then we can work on that. Yeah.
At least on the memory front, 2 different ways to look at that is, one is the energy cost of accessing the memory, but the other way you can look at this is as the system designer who has to buy the memory to put on there. And those are actually different than whether you're paying per cost or per total amount
Per
of
bulk
memory
of it,
available.
yeah. Yeah, these are all very interesting directions.
Anybody else? No? Okay. Thank you very much.
Yeah.